All right, welcome to the last chapter of linear algebra. So we have been focused on this whole time, this idea that we are going to solve all equations ax equals b. And what this chapter is going to talk about is going to be, what if there is no solution to ax equals b? So my guiding example here was trying to find a solution to this system. And you go ahead and do our usual thing where we row reduce. I'm getting this row of zeros at the bottom, which is not what we wanted when we have a pivot in the augmented column. So this system has no solution because the row reduced matrix, augmented matrix, is inconsistent. So what this chapter is going to look at what happens if we still want to kind of have a solution, or we want to represent something that could serve as a solution to a system that has no solutions. So we want ax equals b, but there is no x, no solution. So there's no solution that makes the system work. Okay, so we are going to find then an a times some other vector then that is closest, a times x that is closest to b. Okay, so we're kind of, our whole goal for this chapter is going to be, how do we determine what this vector x hat should be so that when I multiply it by a, we get something that is close enough to our intended goal, which was b. Okay, so the first thing we're going to do is we're going to develop this sense of closeness. And so 6.1 is going to feel very much like a review of multivariable calculus, because it is an idea about, we measure closeness through some of our vector geometry. So we are going to talk about three things today. The dot product, we're going to go back to that. We're going to talk about length and unit vectors. And then we're also going to talk about something called orthogonality. But really, we've already talked about our how to know if two vectors are orthogonal, or aka normal. So this is going to feel like a review of multivar, which is why we're doing it now. And then in later sections in chapter 6, we're actually going to talk about how do we determine what will be closest to what we are looking for. All right, but today, some review. So we call some of these operations different things in linear algebra because they don't work exactly, or they're not represented exactly the same way they were in multi. Okay, so here we have the inner product, okay, but it's also the dot product. That is exactly the same. The key here is, though, that I can't, the way the vectors are written, when they're written like this as n by 1 matrices, I can't actually multiply them together. Okay, so the dot product, if I wanted to dot u and v together, really what that means is I am multiplying u transpose, and I'm actually not going to put a multiplication symbol because we're kind of running out of multiplication symbols here, u transpose times v. That way, that ensures that the columns and rows match for my multiplication, because this is still matrix multiplication. So the columns and rows have to match. We cannot, in fact, if like this does not, we could not just do like u times v. This is not possible because that's not a defined method of multiplication for matrices. So thinking about that the dot product of u and v, two vectors that we're representing in linear matrix algebra, is actually u transpose, so tilting it on its side like it's written down here, and then multiplying it times v, which is right here. Okay, it means the same thing. it still results in a scalar, and hopefully that is familiar. So if we multiply all components, sorry, not all components. Oops, excuse me. Try that again. Multiply corresponding components and add together. Okay, so we're still getting a scalar out when we do an inner product. Okay, and then just to review, just to review a couple of properties. So we've got the symmetry axiom where the order doesn't matter. This is the same as thinking about the commutative property. Here we've got the additivity axiom, which is basically the distributive property. And the homogeneity, meaning that C is a scalar here. This is the associative property. But I left some extra room here because I want to combine. We'll need this a little bit later. I want to combine B and C. Okay, so the idea is that let C1 through, let's say CP to be constants, and and U1 through UP to be vectors. Okay, then C1, U1, if we multiply the constants with their corresponding numerical vector, and we add all of those together, CP, UP, and then dot it with some vector W, okay, that will be the same as me dotting each of the vectors with W first, and then scaling them afterwards. Okay, I think that intuitively makes sense, just kind of from the two previous axioms. It's just kind of a larger scale distributive and associative property, but just let's think about that. We will probably need that later. The last one is a little bit different, and we want to kind of think through why this must be true. So this says that the dot product of a vector in itself must be greater than or equal to 0. If you've forgotten how or why this is, let's just write it out really quick. So if I have a vector dotted with itself, then that would mean I was multiplying each of the corresponding components and adding them all together. So that would be U1 times U1 plus U2 times U2 all the way up to UP times UP. But that could also be represented by U1 squared plus U2 squared UP squared. And if you're adding together the sum of squares, it must be greater than or equal to 0. And the only time that it would be equal to 0 was if U was in fact the 0 vector. Okay. All right, so some axioms just to review. All right, and that was our inner product / dot product. Now, length of the vector, okay, we're using a new term here called norm. That's really just the magnitude. That is not different at all, okay? It is non-negative, meaning that the magnitude of a vector, considering it's kind of measured from the origin outwards, is going to be non-negative. It's going to be 0 or it's going to be positive. And we can get that from the fact that the magnitude is defined by the square root of the vector dotted with itself. Using the representation we just did on the last page, that's a sum of squares, okay? And the square root of some kind of sum of squares is going to be a positive. And no, we're considering it to be a positive number because we're considering it as a distance, kind of. And helpful later, the magnitude of some vector squared is going to be the same as it dotted with itself, okay? For a scalar, note, you can take a scalar out of the magnitude, but since the magnitude has to be non-negative scalar, when you take that scalar, the the magnitude must be non-negative scalar. So if you are trying to factor out a constant, then that means that you have to put absolute values around that constant. And there's a proof for that on the field notes. I don't think it's really necessary for you to kind of draw it out. It's just kind of from a concept I know we learned in like algebra 2. So just thinking about that. And let's see, distance, okay? The distance between two vectors, looking here, is the magnitude of one vector minus the other. Okay, so it's, and this is, and I know some of this is a little bit confusing, but the distance between, I want to make sure we know the ends of those vectors. Okay, and you can either think about that up here as kind of thinking about the Pythagorean theorem, but you can also think about, remember, if I've got, let's make a little diagram, a vector v here, and I get to use all these fun colors, a vector u here, then this segment, I want to represent this distance in between them. It will be the same as a kind of parallel distance over here if I draw out negative v. So this would be u minus v. Okay, these two are going to be the same lengths. Okay, so the distance is going to be the magnitude of u minus v. All right. So real quick, I guess we'll just do one example here. So if we're trying to find the distance between these two 5-dimensional vectors, and a good question would be, what does that even mean? What is the distance, quote unquote, in between vectors in R5? Kind of an interesting thought experiment there. What does it mean to be in 5 dimensions, and how do I measure distance between those things? But trying to find the distance between two vectors, I'll call this one u and this one v. So u minus v, okay, just for simplicity, is going to be 3, 2, negative 3, 0, negative 3. And then I need the magnitude of that. Okay, so kind of the sum of squares, 9 plus 4 plus 9 plus 0 plus 9. All right, so I've got 27, 31, square root of 31. Okay, distance between those two. And again, kind of thinking about the fact that the distance between two 5-dimensional things can be reduced to some scalar. What does a scalar even mean? Just some meta questions for you. Okay, other things we needed to talk about, because now we've got the dot product, we've got the distance between vectors. Okay, so you can see how we're kind of starting to measure closeness. The other thing we're going to need as a tool for later is how to prove that two vectors are orthogonal, which we have already done. But here's a new way to do it. Okay, from geometry, two lines are geometrically perpendicular if and only if the distance from u to v, okay, is the same as the distance from u to negative v. Okay, so that's saying that here and here have to be identical. Okay, now the way that they're intending to prove this is also by thinking about making perpendicular angles. Okay, we can think about that later. But let's walk through kind of just using the distance formula proof, and then we'll talk about where does that right angle orthogonal come in and where have we seen that before. So if I'm trying to find the distance in between u and v, and then I square it, starting here, okay, that's the u minus v magnitude squared. Now, from the first page, the definition of that was just u minus v dotted with itself. Okay, so this is like from page 1 of the notes. Okay, all right. Now, if I distribute, because the dot product is distributive, okay, the second step is u distributing. So dotting u with u minus v, and then adding that to negative v dotted with u minus v. Okay, distributing again in the third step. Okay, u dotted with u minus u dotted with v plus negative v dotted with u plus v dot v. So here, I'm sorry, this line is supposed to be, look a little different. Let's change this up. This line is supposed to say magnitude u squared plus magnitude v squared minus 2u dotted with v. Okay, so just combining like terms, representing u dotted with u as magnitude u and magnitude v. Okay? All right, so this means this is our conclusion that we got here. But if I do the distance, if I know that these things are going to be the same magnitude, this formula should be the same, should work out the same steps. It's if I found the distance in between u and negative v. The only thing that would change would be the sign of the 2u dotted with v. So these two things are supposed to be equal. So let's compare that. Okay, so if those two things are supposed to be equal, then that means that magnitude u squared plus magnitude v squared minus 2u dotted with v, it should be the same as magnitude u squared plus magnitude v squared plus 2u dotted with v. Subtracting everything that is in common, that means that negative 2u dotted with v should be equal to 2u dotted with v. Now the only time that the dot product will be equivalent but the opposite sign, okay, this one's negative, this one's positive, is if the dot product is 0. So the only reason that this step would occur, knowing that they're supposed to be equal, is if u dotted with v was equal to 0, which is exactly what we proved in multivariable calculus for knowing that two vectors were orthogonal. And you can think about that, you can go back and be like, okay, we thought about angles, we talked about the other definition of the dot product that had to do with the cosine of the angle in between them. But again, this is us using the distance formula between two vectors to prove that in order for two vectors to be perpendicular, okay, we know that their dot product should be equal to 0. Okay, u and v are orthogonal. Okay. All right, so one other thing though, but if u and v are orthogonal, then our formulas from earlier get a little bit simpler. U dotted with v is equal to 0, which means that the distance between u and v, so magnitude u minus v or u plus v, it doesn't really matter. I'm going to go with u plus v. That would be like u minus negative v, is equal to magnitude u plus magnitude v. Sorry, that doesn't look like a v. But this is the Pythagorean theorem. This is a squared plus b squared equals c squared. Amazing. Okay, so if u and v are orthogonal, that's why we can use the Pythagorean theorem to determine the length of different sides. Okay, so in the practice down here that I was going to ask about, and I think we'll do just, actually, I'm going to leave this to the field notes for this one because doing the dot product and measuring distance should be pretty easy, so I don't want to do a lot of time in the lesson for that. But determining whether the given vectors are orthogonal, you have two methods. Okay, you can either, one, do the Pythagorean theorem and check to make sure that the Pythagorean theorem is true or false. If the Pythagorean ends up being like false, then you know that they're not orthogonal. But I think shorter, I don't know why you would use the Pythagorean theorem when we can just do the dot product. Okay, or in this case, now that we're in linear algebra, calling it the inner product. Checking that inner product equals 0. All right, last page. Okay, and this is the part that I wanted to talk about. That's a little bit more than what multivariable calculus was talking about. Okay, the orthogonal complements. So this is going to be analogous to when we talked about the normal vector in multivariable calculus. Because the idea was that we found one normal vector in multivariable calculus. Now I am looking for all of the normal vectors to a subspace. Okay, in this case, in 3 dimensions, as displayed here, the subspace is a plane, and I'm looking for what are all of the vectors normal to that plane. There are so many, which is why we want to describe it in some kind of, with a basis, and this is why we're going back to chapter 4, or I want to describe it as a some kind of scalar or parametric set of solutions. So the vector z is orthogonal to every vector in a subspace. Okay, and this here we've displayed it as a plane because that's the easiest to visualize. If it is orthogonal, it's said to be orthogonal to the whole subspace W. The set of vectors that are orthogonal to all of W is called the orthogonal complement and is designated by what looks like an upside down T, but really that's the little like orthogonal symbol. It just doesn't have a little right angle looking thing there. Okay, so this is W perp. I know, another fun word. So what we are going to do in this last example here is review how to write a basis for something so that then you can think about, okay, well, this is going to be the orthogonal complement to this other set. And this has to do with thinking about, remember from the first page that when we're talking about the inner product, proving that 2 vectors are orthogonal, that matrix multiplication is actually U transpose times V. Okay, so the orthogonal complement of the row space. Notice the row space. So thinking about, again, the rows going sideways. The orthogonal complement to the row space will be the null space of A. Okay, so thinking again, the null space of A would be all vectors. Let me write this down. The null space of A is all vectors when they get multiplied by A, all vectors X. There we go. So that when they get multiplied by A, when each X gets multiplied by the rows of A, they get mapped to the 0 vector. AKA, when X is multiplied by one of the rows, I get out 0, meaning it is perpendicular to each row. Okay, and the opposite, if I wanted to find the orthogonal complement of the column space, then I have to transpose A, switching the rows and columns, and then find the null space. Okay, but again, this has all to do with the fact that we're using the null space as the orthogonal complement because I want to multiply a vector times A and get out 0. Because that's like me dotting X with all of the vectors in A at the same time and getting out 0 for all of them. Okay, so if that makes sense to you, yay. If not, write it down and we'll try to go over it in office hours or in the lesson. But really, we've got a nice note card formula here. So again, the orthogonal complement of the row space of A is the null space of A, and the orthogonal complement of the column space of A is the null space of A transpose. And that has to do with these 2 facts here. To test that something is orthogonal, you take the dot product, which really means you multiply the transpose of one vector by V. And to do that, if we're trying to do that all at the same time for all of the rows or all of the columns of A, really I'm just trying again to find solutions to AX equals 0. So let's work on this problem and writing a basis because I think we need a little bit more practice with just writing a basis for something. Okay, so A says find a basis for the null space of A. Okay, so that means I need to find the null space and then find vectors that will describe all vectors in the null space. So a basis for the null space will be all solutions to the equation AX equals 0. So here's A, and I row reduce, and I get 1, 0, 0, 0, negative 1, 0. Okay, so that gives me vector solutions that look like, I've got 2 free variables here. So I've got x2, actually, yeah, I've got 2 free variables, but x1, notice, is not dependent on x2. So that means x2 is just doing its own thing. Nobody else gets influenced by x2. x1 is influenced by x3 though. Remember I had to add this to the other side of my equation though. So 1, 0, 1. Okay. So again, forming a basis. Vectors that will span the entire null space, meaning vectors that will make up X. So the basis for null A, 1, I need them to span the null space, and 2, I need them to be linearly independent, but that's going to be this vector and this vector. That's the basis for my null space. Now, what is this? Okay, what shape is it? This is a plane. The span of two vectors is going to be a plane. What dimension is it in? R3, because they have 3 components. What else is this equal to? Okay, we just found a basis for the null space. This will also be the basis for the orthogonal complement to the row space. Okay, because each of these vectors here, or any linear combination of those vectors, when I multiply them by A, I will get 0. Meaning, when I dot each of these vectors with each row of A, I will get 0. Meaning each of these vectors is orthogonal to each row of A. Okay? All right, I'm going to leave B to you. I'm actually going to skip to D and make that the last example we do. Okay, so I want to find a basis. Actually, sorry, I don't want to do D because we just found a basis for a null space. So let's look at C. Okay, I'm looking for a basis for the column space. So in this case, I am looking for vectors that will describe any linear combination that I can make out of these 3 columns. Well, one hint you should already know is that it's not going to have column number 2 in it. A 0 vector is not a linearly independent vector at all, so I can't include that column in my basis. But I do want to see which columns are linearly independent. You actually already did this. Okay, so by row reducing in problem A to this matrix, you were able to see which columns are linearly dependent or independent. And actually, in this case, it doesn't really matter. You can use column 3 or column 1. For simplicity, though, we're going to go ahead and use column 1. Okay. Now, if I want to write a basis for the column space, I need to go back and use the original linearly independent vector, or excuse me, linearly independent column. If I just use the vector 1, 0, the span of 1, 0 is different than the span of 1, negative 2. Okay, that's the simplest way we can put it. The span of 1, 0 will only include non-zero entries at the top. I want non-zero entries in the top and the bottom. Okay, which is why I need to go back, and when I'm writing a basis for a column space, do not use the final columns. Use the original columns. The only reason we row reduced was to test which of the columns were linearly independent, so that when we wrote a basis, we knew we were using linearly independent vectors. So the basis for column space of A is actually just one vector. Okay, the original column, 1, negative 2. Okay, and what is this? What shape is this? Well, it's 2 dimensions, so I know it's an R2, and the span of one vector is a line. Okay, so this is a line in R2. Okay, so a little review writing bases. To sum up what we did today, because that's it, we had at the very beginning, we talked about where are we going in this chapter? What's left for us in linear algebra? And it's the idea that if we have no solution to a system, we need to get as close as we possibly can to having a solution. So we went back and we reviewed several things from multivariable calculus that we will need as tools going forward. We reviewed what the inner product was, which was just the dot product. We reviewed how to find the length of a vector, which will be helpful later when we're determining literal distance between a vector and the vector we're looking for and what solution we can actually get. We also talked about orthogonal vectors, which is really important also to thinking about distance or thinking about how we can travel from the intended solution to a close by solution. And we once again proved that in order to prove that two vectors are orthogonal, we need that their dot product is equal to 0. And then we tied this all back in to what we were doing in chapter 4 and 5 by writing a basis for the orthogonal complement, writing a basis for all vectors that are orthogonal to a certain subspace. And we put down two definitions for our note card, was that the orthogonal complement to the row space is just the null space of A, and the orthogonal complement to the column space is just the null space of A transpose. And then we reviewed how to find a basis. Okay, that's it for today.